Hello, everyone. This is Raphael from the HM Academy. Devrel here. We have another great talk this week with Johan from Certora. Um, Form verification is a very complex term, but it's another way for us to fully fledge and test our DeFi apps and especially our hooks. So this talk will get us more into that and see what Sator brings to the form verification reigns. So Johan, please take it away.
Yeah, thank you. I'm Jochen Hünecke, and I'm a formal verification researcher at Certora, and this is my contact detail. So I want to talk about formal verification. So let's start with the definition of formal verification. This is taken from Wikipedia. So formal verification is the act of proving or disproving the correctness of a system with respect to a certain formal specification or property using formal methods and mathematics. So it's not about testing but about proving that your system, your program, your smart contract is correct and showing certain properties. So you have to first figure out what are the important properties of your smart contract that you want to show, and then you can use formal verification to prove that they hold. So there are some statements about formal verification, maybe also some myths. So here is a slide that shows 3 statements about formal verification that you often hear. 2 are true and 1 is a lie. Maybe you can see it. So the first statement is formal verification can find bugs. The second statement is formal verification can mathematically guarantee that your protocol will remain solvent, or whatever property you like. And the third one is formal verification is hard and require a PhD to succeed. So think about what you think is a true and what is a lie. So if you think formal verification can find bugs, then you are right. So you can use it to, for example, find rounding errors. You have a reason about rounding errors and find rounding errors that go in the wrong direction and can be hacked to gain funds from a contract. It can figure out strange edge cases that in some state of the contract, if you tweak it right, you can actually, or if you are unlucky, you can actually lose shares even though you deposit some funds to the contract. And things like these could be stated as properties, and it will find these bugs. Sorry. Well, no.
Yeah. Also, I dropped a message. So
Sorry.
feel free to ask any questions anytime.
There was a alarm going off in the background. So So what is most important is that you can actually fix your problems after you find these bugs, and then you can redo the formal verification and check that your fix is actually fixing the bugs. Yeah, the second statement was that formal verification can prove things like solvency and other properties, and we have demonstrated in the past that it's actually possible to do so. So, for example, we proved solvency in Uniswap's AMM, that the contract has enough funds, regardless of what transaction occur. And the last statement, that formal verification requires a PhD to perform. Yeah, this is the lie here. So if you can write solidity, you can also write you can do formal verification. So this is our formal verification language CVL. I don't want to go into the details of the code, but you can see it looks similar to Solidity. You can declare variables, you can call functions, and then you have a property that you want to check after you do all the transaction, and it looks like a unit test. But in contrast to a unit test, it doesn't check one behavior. It actually checks that your contract is correct, regardless of how it was set up, and regardless of the arguments of the transactions, of the input values. So how does formal verification work? So we, our tool takes the smart contract in form of Solidity files, and it takes a specification, which is in a special language CDL, which we just saw in the previous slide. And these are put into the tool. You will run the tool, and after a while, it will tell you either that your property holds, and this gives you a proof that your smart contract will fulfill these properties under all inputs. And the other outcome is, of course, a counterexample where you see for this particular input, if we start it in this state, then something bad happens. And there's also a third output that I didn't put here, which is the timeout, which is unfortunately unavoidable. We can't do magic here, so some problems are too difficult for the solver, and then it will just don't give you an answer, and then you have to figure out how to improve it. So how does it look if we go more into the details? Well, I don't want to go deeper than this. So it translates the code, the Solidity code, and the specification in the end to a logical formula. And this logical formula basically states that your contract has a bug. So it has the logical formula is a large formula with a lot of variables, and if it's true, then your contract has a bug. And then we just give this formula to a solver, a formula solver. There are off-the-shelf formula solvers that we can use, and they will find variations for all the variables in your contract, like the input variables, and the current state of the contract, but also the intermediate steps. And if it can find one, then you have a counterexample, and it will print this. And if it doesn't find, if it finds a proof, a mathematical proof that the formula doesn't have any inputs satisfying it, then you know that the bad behavior cannot occur. So let's do it with a simple example. This is a function from the pool manager Uniswap v4 pool. This is a function that can be called by anyone after he locked the contract to take out money if he has, for example, received the money due to a swap. And it takes as argument the currency, the user that should receive the money, and the amount. The currency transferred just transfers the token to the user, and the account delta should update the internal balance of Uniswap and make sure that it's accounted correctly. And from the point of view of the Uniswap contract, you want to know that this accounting is correct. So how can we do this? So how do we know that this function take updates the account's liabilities correctly? So the question here are multiple. So for example, is this unchecked dangerous? Can this unchecked basically do some math that goes wrong? There could also be a logical error. For example, maybe this minus sign is the wrong and it should be a plus sign. And these are the questions we want to verify. And to verify this, we need to write a specification. It's like a unit test. So the specification in this case could look like this. We have this keyword rule, which basically says this is a specification. It's similar to the entry function of a unit test. It takes as arguments some values that it can use, and these values are initialized. So basically our prover tries every possible value for these arguments. And it does it symbolically, so it won't take forever. And otherwise, it looks like a unit test you can call solidity functions. In this example, we call the function get delta to get the current liabilities of the user. Then we call the take function, and then we call get delta again to get the new liabilities, and then we can reason about the difference between the return values of get delta. We also have an environment, this NFE, which is our way to say who is sending the transaction, where does the transaction start, where does it end, in which block was the transaction included. So the NFE basically encapsulates several things about the transaction, like the message sender, which we use here. And you can use as many environments as you want if you want to simulate multiple transactions. So in this case, we only want to simulate one transaction, so we only have one environment. And then we have mathematical integers, and these help us to reason about the real mathematical property. So if we would use these UN256, then we would basically have the same problems in the spec as we have in the contract. And if we then write an assertion, then it wouldn't detect overflows because you have the same overflows in the spec. Instead, we don't use these bounded types, we use mathint, and these are unbounded math integers. They can grow arbitrarily large and never overflow. And we can do this because we reason about them symbolically. And actually for the solvers, mathints are even easier than UN256. And this means we catch overflow bugs, for example. And then we have an assertion, and the assertion is basically the property that we want to show. So if we write require, like in Solidity you write require, then it's an assumption. So if it's not fulfilled, then in Solidity the transaction will stop and nothing bad will happen. And in CVL we also stop and just assume that everything is fine. If we want to say that something must not happen, then we use assert and say this is a property that we want to verify, that we never run into a problem. And we prove this property here for every input and also for every starting state of the contract. So we don't need to set up the contract. We don't call constructor, we just assume that it starts with some arbitrary values for all its storage variables. So let's do it on a hook example. So I just took as a running example the hook that is in the Uniswap v4 guides. So if you open the Uniswap v4 guides, you find one example for writing a hook, and this is the points hook. And this is extending base hook. Base hook is basically the base class that you write for all your hooks, and then you can do functions like after swap, before swap, to get notified whenever the swap happens on your pool. And you not only get notified, but you can even change the behavior of your pool, and you can either change the amount of tokens that are swapped with the pool, or you can put more tokens in the pool, or you can do some arbitrary side actions. And here, this is a simple example that as a side action rewards the user for swapping on the pool. And it does so by minting a points token for the user, and should mint as many tokens as the user spends on the pool in Ether. So the idea is that you figure out what is the user, and the user has to tell it by putting his address in the hook data. And if he does so, he gets a reward, and the contract figures out how much Ether you are spending, and the same amount of Ether is then minted as a token. And we have another hook on add liquidity, which works actually exactly the same. So instead of on swapping, it's now whenever the user adds liquidity, and if he puts Ether in the pool, then he gets as much reward tokens as he puts Ether into the pool. And this is the desired property. If we swap or if we add liquidity, the user should receive point tokens for the Ether that he puts into the pool in a 1-to-1 ratio. So this is a property we want to show. And the first thing is when we want to show this for a Uniswap hook is we have to figure out that the hook doesn't live in its own world. So it's not a standalone contract. It's connected to the Uniswap pool manager. And if we look at the full picture, it becomes quite complicated. So we have a user. The user uses some router, for example, the Uniswap universal router. And this router performs the transaction. So it swaps tokens. It sends the token to the pool manager and tells the pool manager to swap these tokens. The pool manager notifies the hook that there is a swap going on. It performs the swap in the pool, and the universal router sends the token back to the user. And to illustrate this more clearly, I asked an AI to draw a picture that shows the messages that go around between user, router, pool, and hook. And this is a picture that I got. Yeah, it's an AI picture that you can clearly see because the hand has 2 thumbs. But yeah, it didn't. Otherwise, the AI quite failed because what I really had in mind was this picture, which I had to draw myself. So we have the user, we have 3 contracts, the router, pool manager, and hook. And what the user does, it executes a transaction. The router locks the pool manager, it does the swap. On the swap, the pool manager tells the hook that we now have a swap. It calls the before swap hook. It performs the swap, calls the after swap hook. And then the router settles with the pool manager the tokens. So settle makes sure it sends the token from the user to the pool manager, settles it, takes the tokens out. We have seen this function earlier, and sends them back to the user. So in fact, we don't need all the contracts if we want to verify this property. We can just focus on this part, on the swap part itself. And this is what we do. So we focus our rule on 2 contracts, the pool manager and the hook. And we just start with the swap function of the pool manager. And this will call the before swap and after swap of the hook. And then we can reason about what happens if we swap. And this is still too complicated because the swap function is a very complicated beast in Uniswap v4. You probably have heard of the curves that are used to determine how much tokens are swapped with Uniswap. There's a lot of math going on. There is nonlinear math, which is very difficult for solvers. And frankly, we don't even need it because we are just interested in how many Ether were spent and how many points token he got. We don't care if the amount of tokens he received is fair or something. So we will just abstract from this swap function. And then our rule is not too difficult. So this is slightly simplified, the rule. So we have these summaries, which we use for swap. And then this is a rule where we say, we call the swap function. And before we call the swap function, we ask pool how many tokens it currently has. And we ask the tokens how much token we have already minted by asking for the total supply. And then we call the swap and we ask for the tokens in the pool again and for the tokens that we minted. And our property is that the difference in the Ether balance should be the same as the number of points we minted for the user. So yeah, let's do it with a
Before you
demo.
start, it seemed like a lot of these tests seem really straightforward. Like they're not super complex. Looks like what I would write in a Foundry test.
Yes,
Uh,
yes, this is the intent of them.
cool, cool.
So, but the main thing is that for a Foundry test, you have to set up your test. You have to set up the pool, you have to put some tokens in. And then you have to, you have to simulate a user that swaps tokens. And maybe you even have to pick the values for how much tokens you want to swap. And we don't have this set up. And we verify it for every possible state of your Uniswap pool. It could be that there are already 20 different pools using the hook, and then the bug occurs, and we would catch it because we start with an arbitrary state. And we also check all possible input values. So yeah, this is the VS Code, the points hook from the Uniswap example. It's a bit more complicated because what I didn't show is that it actually checks that we are using Ether as currency, otherwise you don't get rewards. And it also checks that you buy that you swap Ether for the tokens. So it doesn't have the bug that was on the slide that it would give you a negative amount of tokens. So yeah, this is a real function, and the specification is also slightly bit more complicated. I mean, this part here is the same that was on the slide, and this part also. But we have more preconditions, namely that the pool must use Ether, otherwise the hook wouldn't be called and the property wouldn't hold. It must swap the 0 for 1 flag must be set, so it swaps Ether for the token. And we also need to know that the hook is active, that the pool uses the hook, because if the pool doesn't use the hook, then you just get a counterexample. And yeah, now we can run this with the Certora prover. So we have a script where you can, with a Certora run, which runs the prover. I've set it up all correctly. We need a configuration file that basically says what is the Solidity file and what is the spec file that we want to use, and some setup, for example, the paths and which Solidity compiler to use, some other prover options that you want to use. I wanted to run it on the cloud, so let's do it on the cloud. So you can also run it locally. Know that our tool is open source, but it's much more convenient to run it on the cloud. And this will tell you it now submitted the solver to the proof to the server, and it gives you a link where you can see the progress of your rule. And then you can go to a browser of your choice. Let's say here. And you see it takes a while for the cloud to pick up the job. And since it takes a while, I just do it like in a cooking session where you just take the pot out of the oven and then you see the result of your prover run. It doesn't take so long, so it just takes 6 seconds, but because if there's a lot of traffic on the server, then the runs are basically queued one after the other. And I think 6 seconds is also only the part for this rule, and it needs a bit of pre-setup. But it takes 2 minutes or so. Now we get a red cross, which means our rule is not correct. And now we can try to figure out why the rule is not correct. And what we see here is we get a counterexample. This is a call trace, but you can see it like a trace of running through your program. through the whole rule, I should say, because first we set up the rule parameters. You can see the variables if you want. Here's a variable, so you see, for example, the balance, ether balance before was 3499, the ether balance after was 3498. No, the other way around. Before it was 3498, and then we minted one, swapped one ether. So we should have gotten one token. But these values didn't change. The prover just generates random value. And this is something that is sometimes a bit confusing because these values are often very ugly. But you see somehow that these values look very similar. We can also look here in the run what happens in the end. So the assert failed. So it was false. And we can see that there was one ether. The difference on the left-hand side is 1, and the difference on the right-hand side was 0. So somehow the points were not minted. That should have been minted. So we can go into the swap and then see the call. So we see here the the pool manager swap. Here we call it, I wrote a harness that just makes a few functions of the pool manager visible, but otherwise we use the standard Uniswap pool manager. Then it checks that it's unlocked. This was true. Then it calls the before swap hook. Well, this before swap hook is not existing in the function, so it just returns. Then we do the swap summary, which is my abstraction of the swap that I mentioned earlier. And then we call the after swap. And we see the after swap hook was never called. And yeah, and the reason the after swap hook is never called is because I think in this case it's because the message sender is wrong. We can actually see why it didn't call, because we see here there's a branch condition, and then we can ask where is this branch condition in the source code. And it will take us directly to the source code of Uniswap after swap. This is the hooks.sol in v4 core Uniswap. And it checks is the message sender self, which is the hook that we want to call. And Uniswap has this feature, if a hook swaps on its own pool, it doesn't get called back. So you don't have this reentrancy. So what we can do now is we can we can add a precondition that the message sender is not the Uniswap hook itself, that the points hook that we just wrote. So yeah, there's a question, what is the benefit of using this formal verification rather than a Foundry test? So the main reason is, I'm not sure if you would find this with a Foundry test, because you would probably not think of setting up your contract like this, that the message sender is the hook itself. And maybe this hides a bug. In this case, you probably are correct saying, well, my hook doesn't call any swaps, so I am safe. But maybe you write a different hook that calls itself, and then you would want to know about this bug. So what we can do is we can fix this bug. Basically, we add a new require. In this case, we want to say that the message sender is not the current contract. And there's a similar bug that you then get. I think I don't have the run for this, so I just say what the bug is. So the other problem is that a Uniswap hook must be on the right address. If it's on the wrong address, then it's not using the right permissions. It doesn't have the right permissions. So for this I just wrote a public function to check that the hook is on the right address. It calls the validate hook address from the base hook. And I just require that this is true. And if I then run the solver again, yeah, I will just cheat and show you the run directly. So this is, in the end, you get the green check mark. That means your contract is actually verified. Yeah. So let's go back to this. There's another thing about this check hook address. Normally, you can't deploy, or the hook itself makes sure that it's never deployed on the wrong address. So the constructor will ensure that check hook address is always set correctly. However, our tool starts with an arbitrary state and it ignores the constructor usually. So this is why you get some false counterexamples that cannot happen in practice. And what you can do then is you can tell our prover these are the properties that will be ensured by the constructor and they will never be violated by any rule that comes after the constructor. And if you do this, then it actually checks your property, and we call it an invariant, or it's called an invariant informal verification. A property that should always be true. It starts true after the constructor, and it will never be violated by any public function that we call. And we can do this and say, yeah, that the hook is correctly deployed as an invariant, and the invariant basically is the property that check hook address returns true. And if we do this, then we can just mention this invariant here and say we require the invariant that the hook address is correct. And yeah, and this is no longer an assumption. So we don't need to assume that the hook was on the right address, but we know the constructor will already ensure this and it will never be violated. And if we run this through our prover, then we get again the green check mark for the swap, and it will also check the invariant itself that it's always true. And here we get a small warnings, which is kind of typical for Uniswap hooks. And the warning is that there are a lot of functions that are always reverting. So we don't have a remove liquidity hook, so it will always be reverting. And if something is always reverting, it's always a kind of, yeah, almost a red flag for us, because there are often bugs where you put too many assumptions in your rule and suddenly all the runs are reverting. And to find these bugs easier, we check by default these sanity checks where we check for every rule, is there a run such that it succeeds? And this also allows us to, for a run rule that succeeds like this one, we even get a counter example, so to say, an example where it succeeds. There's an assert false in the end, which is something that our prover just inserts to make sure that we get a counter example. But it's really one run through the contract where the rule is satisfied. So we see that the balance, if we go to the variables, we see that the balance, difference was 0 before and it's 0 afterwards. So the rule is correct. It's often a boring example.
We have another question. Uh,
Yes.
so two questions. Is it possible to use form verification on complex code bases efficiently? Considering current AI status, is it excuse me, is it effective to tear apart invariants and feed AI models for better results?
Um, Maybe the first one. So I start with the first one. So if you have a complex code base, then it's possible to use formal verification efficiently, and you do it by doing abstraction. And this is what I did for the swap, for example. And maybe this is a good time to see what I did for the swap. So basically, I said the swap function itself of the pool manager is a very complicated beast, and I want to replace it by a simple swap summary. So I basically remove the function from the Uniswap contract and replace it by my own CVL function, which is much simpler. And this CVL function kind of simulates all the behaviors that the Uniswap pool can do and some more. So by doing it this way, this we call over approximation, we can be sure that if we prove that the contract is correct, it is really correct. But if we get a counterexample, it can happen that we get a counterexample that is not a real counterexample. For example, we could get that you swap 50 Ether for $1, and in practice it doesn't happen because the ratio between Ether and dollar is not 50 to 1. Yeah, and the trick to do this is we use, again, uninitialized variables. So we just guess the amount of tokens that we want to swap. We have uninitialized amounts, and that means the prover tries every possible value for them. And every possible value is too much, so we need to restrict these amounts further. For example, if we swap the 0 token for the 1 token, then we should sell the 0 token, so the amount should be negative, and we should buy the 1 token, so the amount should be positive. And there's also amount specified, and if the amount is specified, then we don't want to swap more than the specified amount. Uniswap can swap less than the amount if there's not enough liquidity, but it will never swap more than the specified amount. And similar, if the 0 for 1 is false, then here is basically where we get our ETH balance. So we keep track in our summary of the ETH balance because Uniswap itself doesn't do it, but we want to have an easy handle on it. So I just wrote an update to a global variable. It's called a ghost variable because it doesn't exist in the smart contract, but only exists in the verification. And we have finally one condition that is basically that Uniswap doesn't trade more tokens than it has in its pool. So we know this is true because we proved the solvency of Uniswap. And of course, you can have bugs in this writing this summary. So we don't have an automatic method currently that can tell you that you write such a summary and ask, does Uniswap really behave like this? And even if we had Uniswap, would still be too complicated to check it. So this is a potential source of bugs. So formal verification will not give you a full guarantee, but it will help you to find bugs, and it will also help you to think about the protocol more and reason about the requirements that you have for other contracts. So for example, for Uniswap, when we wanted to prove solvency, there are a lot of requirements that you have because for an arbitrary token, Uniswap is not solvent. You need that the token transfer doesn't take fees, or yeah, at least that it doesn't change the balance without any transfer, or that it transfers more than you specify, or you need that no other admin can blacklist your contract and so on. And some of these are even not true for in the real world. But yeah, these are the assumptions, and by writing them down explicitly, you know your assumptions better. So yeah, then another thing is, since Uniswap hooks, there is not only one person writing Uniswap hooks, there are many people writing hooks, and some of the hooks or some of the rules that you want to check are common for all possible hooks. So I have a simple example of some hook rules that are universal. This is the spec file. The other one was a configuration file to list the spec file. So let's look at this rule, this is a rule that tells you your Uniswap hook should only be callable by the pool manager. And this is a very important rule that you sometimes forget, especially if you work with an older version of the base hook. Every public function of your hook, the before swap function should not be callable by anyone else in the pool manager, because otherwise the normal user can go call the function before swap and he gets minted some tokens. Yes, I think this is actually what happened to Cork. There's a question in the chat. And so we can run this rule, and I have prepared it on this current contract. And no, this is not the, oh, this is the wrong one. Yeah. And we see this only callable by pool manager is actually wrong for after add liquidity and after swap. So it can be called by any other contract. And yeah, if we go back to points hook sol, it's actually we override the external function here. And this was possible because we worked with the wrong version of the base hook. So we actually go to the library and we update the source. The base hook sol. No, in the wrong directory. Maybe it's not before core, but before periphery. Yes, this was the problem. And then we run the tool again. And we want to run these general rules. And we should actually get a compile error now, because the new current code doesn't allow even to override after swap. Instead, we have to override underscore after swap. And the same for after liquidity, and that's an internal function. And then we can run the rules again. And now we get basically all green. Yeah, so we had this rule for minting matches. We didn't find a bug during this swap hook. So I also did this for add liquidity. And for add liquidity, I inserted a rule that was very similar to this one. So here, yeah, does the check that the contract is on the right address. It gets the balance before, it gets the balance after, and it checks that the difference is okay. And yeah, then I ran it with the prover. And I was a bit surprised because I got a counterexample even after making sure that it's called. And if we go into the counterexample, then we see that the ether balance is actually negative, the difference of ether balance. And we minted a lot of tokens. And this is an overflow bug. And it's actually in the example book that was on the Uniswap website. So we can find these overflow bugs, and it's not found by a check code because it's an unchecked cast. So if we look at the points hook function, what it does, it takes the negative delta amount 0, and if that is for some reason not negative but positive, then this is a negative number, and we cast it to you in 256, and this gives us this huge number of tokens that we mint for the user. And yeah, if you're unlucky, now the user has full control over your reward tokens. So this is how we can find bugs. And you may ask, why can this happen? Because we added liquidity. Why did the user get tokens back? Why did the ether the ether balance in the pool decrease? And the simple answer is fees. So if the user adds liquidity, he also withdraws all the fees at the same time. And if the fees that he withdraws are larger than the amount of ETH that he puts into the pool, then he gets ether back, and then you have this bug occurring in this hook. And I didn't know that this bug existed, so it was nice to see a bug found in real life.
That's crazy. Interesting, interesting. Ugh.
Yeah. Another thing that I can show quickly. So we have these other rules, general rules, which basically check for every off the hook if it always reverts. And so if we call the before initialize function, so this add with revert basically is like a try catch. So it runs the code, and if it reverts, then it just sets a flag that it reverted, and this flag is last reverted. So you can ask, did it revert or did it not revert? If you call it without with revert, we just ignore reverting paths, and by calling it with this flag, we do a try catch, and then you can also reason about reverting paths. And here we want to say that if the code did not revert, then we definitely want that the hook asked for the before initialize permissions. Because if you have a before initialize function in your hook and your flag is wrong, then you want then something is wrong with your contract. And yeah, by adding these generic rules for your contract, you can just let the rule run in your CI. And if you then, for example, in points hook, you could say, well, I don't want to swap. I don't want to be on pools that don't swap ether. So maybe I want to move this check to a before initialize hook. So you write a new before initialize hook. You add it to your contract. You require that it's always currency zero is the address zero, that it always swaps on the ETH against ETH. And otherwise it just rejects. And now you check in your code, and hopefully you have a CI set up in the background, and it will run the prover in the background. And then, yeah, you check your pull request on GitHub, and then you, yeah, a few hours later, you get a comment on your pull request, which probably looks like, yeah, will tell you that there was a problem, and it will link to this run. And you can see, oh, the hooks flag set before initialized is wrong. And it will even tell you the before initialized flag is not set. So you get back to the code and see, I have to change this variable.
Cool. This thing like really finds every little thing. Like if you forget, it'll find it. Um, dang.
As long as you think about it when you write the rules. So this is important. So we, for example, we never check that the user that the right user gets the token because we don't have a rule for this. And
Right.
this is like writing unit tests. Writing a good rule is also something that you, yeah, need to learn and
Yeah.
think about the right properties you want to check.
For that hooks rules, is that like open to like the community to like pool?
Um, yeah, I mean, I want to make at least this small specification public.
Hmm.
Um, there is there is something like this only callable by pool manager requires your hook to know the pool manager, which is fine because the base hook knows the pool manager, so you can use it. I also wanted a rule that also checks that you check for example, you may want to have a swap function that checks that it's used by the right router. And then it gets a bit tricky to do it for a general case. So you would need to write this rule basically for your contract that you write itself, because every hook may want to use different routers. These examples, I want to make them public. They are not public yet. But I have here some links. And the example repository here should get this example with the points hook and the fixed version where we actually fix the bug in add liquidity. And it even, yeah, I ran the rule again, and then I needed to fix the rule because now it can happen that the difference is negative, but you don't get any tokens.
This is cool.
And yeah, and this example will also be there. And here are also some other links. So for example, the first link allows you to sign up for the free plan to run the prover yourself. So you need to get a key to connect to our servers, of course. It will give you enough free minutes to play around with our tool, and then you can try it out. And yeah, the other links are also useful.
Cool. Thank you so much. So like for specs, in the examples, do they have like specs for other protocols, like some generic ones that devs build on top of?
Yes, I mean, Yeah, I mean, the CVL by example has a lot of different directories. The Uniswap books is still in a branch, but the others should be there. And yeah, I mean, yeah, examples for checking reentrancy. We have examples that require precise bit reasoning. Basically examples that we ran over during the contract that we found interesting for the community.
Cool. Cool. Thank you. Thank you. Thank you so much. This is amazing. These examples should definitely be helpful for anyone interested in experimenting and fully testing out their hooks or other DeFi projects. If there's any more questions, please jump in um, or type it out. Forever hold your peace. Uh, if not, thank you, Johan. This was amazing. Um, I'm very surprised by form verification all the time and what it can do and how hard that it works to find all these bugs. So thank you so much.
Yeah, thank you for having me here. And it was nice to be able to present this.
Cool. This will be all posted on our YouTube channel for anyone who's interested in rewatching. So please come back again next week. Bye.